Sir, so feel free to start whenever you're ready.
तो किसी को क्या कहते हैं उर्दू से तो प्रॉब्लम नहीं है अभी एनीवन हैव एनी प्रॉब्लम विद उर्दू तो हम लोग जरा आई एम थिंकिंग कि इसको जरा सेमी कैजुअल सा रख लेंगे so if anyone has a problem or has difficulty understanding Urdu we can go for English but if no one has any problem with Urdu we can use both
Sure sir, I don't think there will be a problem. एक थोड़ा सा प्रॉब्लम ये है कि एक पार्टिसिपेंट जो है वो हमारा माजिर जो है he doesn't know उर्दू तो उसको मसला हो सकता है उसने अभी ज्वाइन नहीं किया लेकिन वो ज्वाइन करेगा प्रॉब्लली तो सिर्फ ये एक थोड़ा सा वो है
चलो सही है so before starting okay thanks for arranging this काफी short time के अंदर ये अरेंज हुआ है और ये सारी हसन ने मुझे मेरे पीछे पड़ के ये लेक्चर सीरीज अरेंज करवाई है but the thing that we are thinking because if you guys are interested in understanding some cosmology तो मैं इसको थोड़ा सा सेमी फॉर्मल सा रखूंगा लाइक बहुत फॉर्मल सा नहीं रखूंगा so if you have any questions if you want to discuss any topic वो टॉपिक आप सजेस्ट करके मुझे बता सकते हैं and then next time we can discuss those topics specific topics लेकिन what I am thinking is to give you a generic overview I can talk directly about what are the research trends in cosmology but in astrophysics लेकिन it would be very difficult at this point to understand without a basic understanding of physics of relativity and cosmology. So my point is what we can do if we are going with for 2 to 4 to 5 lecture series, I can discuss about some basic stuff in the first few, or once we go along. आखिरी चैप्टर के आखिरी लेक्चर के अंदर आई कैन टॉक अबाउट सम रिसर्च ट्रेंड्स और आई थिंक अभी मैंने ऑर्गेनाइज नहीं किया बट किसी एक लेक्चर के अंदर आई वांट टू also discuss about what are the research methods, what are the statistical methods in cosmology. So agar aap log mujhe one by one everyone can give me the introduction, a quick and brief introduction ke what's your name, आप क्या कर रहे हैं, आपका मेजर क्या है, and like whatever you want to discuss, just for me to understand कि कौन participate कर रहे हैं. So yeah, starting with Hamad. Hamad, why don't you give your introduction?
अस्सलाम वालेकुम सर, मेरा नाम हमाद है और मैं CS 22 के बैच से बिलोंग करता हूँ और नेचुरल साइंस का प्रेसिडेंट हूँ इस वक्त और कॉस्मोलॉजी की टॉक्स में मैंने इसलिए ज्वाइन किया था क्योंकि बचपन से मुझे कॉस्मोलॉजी का एस्ट्रोनॉमी का इन चीज़ों का शौक है तो मुझे लगता है कि इस टॉक से मुझे काफ़ी कुछ सीखने को मिला. थैंक यू.
गुड, थैंक यू. हसन.
तो मैं डबल ई मेजर हूँ, फिजिक्स माइनर कर रहा हूँ और मैंने बहुत मतलब पहले भी कोर्सेज पुश किए हैं ऑफर कराने की. कॉस्मोलॉजी में मेरा इंटरेस्ट रहा है पहले से. मेरे भाई ने मुझे बहुत बातें बताई कॉस्मोलॉजी के बारे में, फिर मैंने खुद बहुत एक्सप्लोर किया है ब्लैक होल्स को, थर्मोडायनामिक्स ऑफ ब्लैक होल्स को और साइंटिफिक मेथड्स में डिफरेंट ब्लैक होल्स के बारे में या कॉस्मोलॉजी के बारे में जो नई ट्रेंड्स आ रहे हैं उनके बारे में. मैंने रिसर्च ट्रेंड्स आ रहे हैं कॉस्मोलॉजी में थोड़ा पढ़ा भी है तो इसलिए मेरा इंटरेस्ट है कॉस्मोलॉजी में. तो मैं इसलिए चाह रहा था ये अरेंज भी हो जाए ताकि कुछ और इसमें प्रॉपर सीखने को मिले.
ओके, थैंक यू. मोहित.
हेलो सर, मैं CS 2022 फिजिक्स मेजर फिजिक्स माइनर अब परसू कर रहा हूँ यहाँ पर हबीब में. प्रॉब्ली नेक्स्ट ईयर तक कंप्लीट हो जाना चाहिए इंशाल्लाह. कॉस्मोलॉजी में बहुत ज़्यादा इंटरेस्ट है. बहुत शुरू से इस पे वीडियोस वगैरह देखते हैं, यूट्यूब के वगैरह वीडियोस तो बहुत ज़्यादा अमेजिंग होती है. लाइक सीकर एक बहुत अच्छा चैनल है यूट्यूब पर जो कॉस्मोलॉजी की चीज़ें बता रहा होता है. उसके अलावा बस कॉस्मोलॉजी का बहुत ज़्यादा शौक है, आगे फिजिक्स का मेजर मास्टर्स वगैरह में करने का सोच है।
ओके, थैंक यू। मुनव्वर।
शायकम, मेरा नाम मुनव्वर है। मैं CS22 के बैच से हूँ और मेरा इंटरेस्ट शुरू से मैथ एंड फिजिक्स की तरफ रहा है। मुझे एज सच कभी चांस तक मिला नहीं कि एक्सप्लोर करूँ ये कॉस्मोलॉजी जैसे टॉपिक्स, तो आई वाज लुकिंग फॉरवर्ड कि यहाँ पे चलो कुछ नई चीज़ें सीखें।
ओके, अच्छा, नेक्स्ट आई थिंक उसैद है या फिर क्या, लेकिन नाम मुईद आ रहा है। but
सर उसैद है, ये
मोहम्मद
उसैद।
उसैद। ओके, नेक्स्ट मोहम्मद अहमद। मोहम्मद।
आपको आवाज आ रही है?
हाँ, आवाज आ रही है।
मेरा नाम अहमद है और मैं क्लास ऑफ 2021 कंप्यूटर साइंस का स्टूडेंट हूँ। इसके अलावा मेरा माइनर है मैथमेटिक्स और फिलॉसफी में, और कॉस्मोलॉजी में ऑलमोस्ट मैं अपनी मैट्रिक क्लास से ही इंटरेस्टेड हूँ। इवन लाइक फिजिक्स में मेरा माइनर या मेजर करने का इरादा था, लेकिन सब कुछ के बाद से। और अच्छा, रिसेंटली चूँकि मैं फिलॉसफी का भी स्टूडेंट हूँ, कॉस्मोलॉजी में फिलोसफिकल पर्सपेक्टिव से भी मेरा काफ़ी इंटरेस्ट बढ़ा है, क्योंकि आज से कुछ अर्सा पहले तक जो कॉस्मोलॉजी होती थी वो फिलॉसफी के साथ काफ़ी ज़्यादा डिस्कस की जाती थी, खासतौर पे इंटरप्रिटेशन वाला जो मामला है इसके अंदर। एक वो आस्पेक्ट में मैं इंटरेस्टेड हूँ, लेकिन जो इसका फिजिक्स से ताल्लुक है कॉस्मोलॉजी का, उसमें भी मेरा काफ़ी इंटरेस्ट है। ये प्रोडक्शन का है।
ओके, गुड, थैंक यू। अलीजा।
हेलो, आई एम एलिजा और मैं CS 2023 से हूँ और मैं साथ में फिजिक्स माइनर भी अभी परसू कर रही हूँ। और मुझे शुरू मेरा शौक एस्ट्रोनॉमी से ही था जब मैं बहुत छोटी थी, लेकिन वो थोड़ा फिजिक्स की तरफ शिफ्ट होता गया। तो लेकिन मेरा एक्टिवली परसू मैंने तकरीबन 7 to 8 years से मैं बुक्स और कोर्सेज ले लेके, जैसे वन ऑफ माई फेवरेट बुक्स वो ब्रीफ हिस्ट्री ऑफ टाइम और इस तरह की बुक्स लेके बुक्स एंड शोज, इससे मैंने एक्टिवली परसू करने की कोशिश की है अपने कॉस्मोलॉजी और एस्ट्रोनॉमी और फिजिक्स के रिजल्ट के फिजिक्स के शौक के अंदर। एंड सबसे ज़्यादा बेहतर थिंग आई थिंक इन द फील्ड ऑफ कॉस्मोलॉजी और साइंटिफिक और फिजिक्स के अंदर यही वाली चीज़ होती है कि कम्युनिटी बेस्ड होती है। सो आई हैव मेट सो मैनी, मेरे ऐसे प्रोफेसर जिन्होंने फिलोसफी में मास्टर्स किया कॉलेज के अंदर, लेकिन हम साथ में बैठ के फिजिक्स एंड एस्ट्रोनॉमी वगैरह पे डिस्कशंस, तो मतलब बहुत अच्छी डिस्कशंस उस पे गई। तो आई एम होपिंग, लुकिंग फॉरवर्ड कि इस सीरीज के जरिए भी ये वाली ग्रोथ होती रहे और डिस्कशन होती रहे ऐसी।
ओके, थैंक यू। उसैद, इंट्रोडक्शन।
जी सर, सॉरी वो मेरा नाम वो मोहित आ रहा है और मैंने वो चेंज नहीं कर पाया, मैं तो
नो
कल
प्रॉब्लम।
ओके सर, सो या माय नेम इज मोहम्मद उसैद, मैं फाइनल ईयर में हूँ अपने, एंड लाइक माय एक्सपर्टीज आर लाइक इन डीप लर्निंग एंड AI, so like I try to like learn more about cosmology because my FYP is also related to that, like so yeah, that's all about me. And I have 2 minors in physics and mathematics.
Okay, thank you. So thank you for your introduction. काफी अच्छा लगा कि all of you have a lot of interest and sincerity to learn cosmology. और it's a fascinating field, no doubt. There are a lot of materials online जो कि कर सकते हैं, but good news is कि if you are cosmologist or if you come from CS or electrical engineering background, believe me, with a CS background working in cosmology or astrophysics, it's very straightforward. क्योंकि आजकल जितना भी काम है, ज़्यादातर जो मेन इम्पोर्टेंट काम है कॉस्मोलॉजी और एस्ट्रोफिजिक्स के अंदर, वो है ज़्यादातर या तो डेटा एनालिसिस का है कि ह्यूज अमाउंट ऑफ डेटा उसमें से इंफॉर्मेशन एक्सट्रैक्ट करना, या ज़्यादातर सिमुलेशंस बेस्ड है कि मैसिव हाई परफॉर्मेंस कंप्यूटिंग सिमुलेशंस जो जो होती हैं उनको कैसे आपने कंस्ट्रक्ट करनी है सिमुलेशंस और अपने मॉडल्स को टेस्ट करना है। और अभी रिसेंटली एक जो AI और डीप लर्निंग की जो बूम आया है, उसकी वजह से देयर lot of people are applying the ideas of AI and deep learning to extract a lot of information from cosmological simulations and from cosmological data analysis. So maybe अभी recently मैंने भी अपनी research direction को थोड़ा सा diversify किया है, and I'm also working on some projects regarding deep learning projects or how to do likelihood free inference from the galaxy data using convolutional neural networks. So I can talk about these things later. So there are a lot of things I can talk about or so इसीलिए मैंने suggest किया था कि we should go with the semi formal type lecture series where you can also participate if you have ideas, if you want to discuss anything, whether these ideas are related to CS and cosmology, physics and cosmology, mathematics of cosmology, or even philosophy of cosmology. I'm also very interested in discussing about philosophy of cosmology. Because I spend a lot of time reading a lot of books on different aspects philosophically, so it's also quite fascinating the area as a. So what I can do is कि अभी फिलहाल इस लेक्चर इसके अंदर जो है हम लोग broadly like अब मैं आपको describe करता हूँ कि होती क्या है cosmology. I can give you some references if you want to go deeper into in mathematics or. But I can tell you that once you have taken some mathematical courses in cosmology, you know like how to derive some equations and how to solve some basic equations. उसके बाद that's enough. एक या दो course if you can do it. There are some good lecture notes online जो कि मैं आपसे share कर दूँगा. If you can just read it, or you can understand those lecture notes. That's all you need to know from the physics point of view. And after that, doing research can be easy because most of the research जो methods use करते हैं, again I have told you कि ज़्यादा data analysis की चीज़ें होती हैं, high performance computing होता है, simulation based हैं, अब deep learning वगैरह के आ गई हैं, तो ये models and tools जो होते हैं ये actually similar ही होते हैं. हो सकता है कि I am thinking about offering a course as well next term. अगर approve हो जाता है and if I have some time, so I am thinking about offering a course on statistical methods and data mining in cosmology and astrophysics. So उसमें I will focus more like 80% on probability theory, statistics, and Bayesian inference, and 20% on the physics. So I think with the people from electrical engineering and computer science background can also benefit a lot from that course. So वो एक काफी उस course को usually like people refer that type of course to astrostatistics. एक new term है astrostatistics की, how you can apply statistics on astrophysical problems. So I want to offer a similar course. If those students who are not in their final year, if they are interested, they can send me an email and tell me that they are interested in that kind of course, so I can develop a formal course on that. So just to give you, let me share my screen और मैं आपको कुछ references वगैरह आपसे share करता हूँ.
Sir, can you see my hand raised? Sorry.
Yes.
तो सर हम ये कर लें कि हम अपना हैंड इस तरह से रेज करके फिर आपसे कुछ पूछें या आप
हाँ you can interrupt me as well or raise your hand, but I cannot share my screen. तो आप कर सकते हो मोहित मुझे sharing I think
सर share content का start वीडियो के बराबर में अच्छा
हाँ
मोहित
disabled है. अभी भी disabled है. Who is the host? Mohit is not the host.
Sir, you can claim host. आप more में जाके claim host करें तो फिर I think आपको allow करेगा.
किधर जाके?
सर मोर में जाके।
मोर तो यहाँ पे नहीं है
सर आप पार्टिसिपेंट्स पे क्लिक करें और उसके नीचे आपको क्लेम होस्ट का ऑप्शन आ रहा होगा।
पार्टिसिपेंट्स को मैंने क्लिक कर दिया। क्लेम होस्ट, ओके गुड। एंटर द होस्ट की टू क्लेम होस्ट की। डू यू नो होस्ट की? एंटर द होस्ट की टू क्लेम होस्ट हो।
सर मैं हृदय से बोल के आपको होस्ट बनवा दूँ। एसएल जो है वो होस्ट कर देंगे, स्टूडेंट लाइफ कर देंगे।
ओके तो जब तक मैं होस्ट नहीं बनता, शेयर स्क्रीन नहीं हो पा रही होती, लेट मी कीप टॉकिंग के। तो कुछ बुक्स हैं, द बेस्ट बुक्स, द बेस्ट लेक्चर नोट्स आई कैन सजेस्ट यू। अगर आपने बेसिक्स से स्टार्ट करना है फॉर कॉस्मोलॉजी, आई थिंक दीज जो बुक्स आपने बताई हैं, ब्रीफ हिस्ट्री ऑफ टाइम और डिस्टर्बिंग द यूनिवर्स, एक और एक जबरदस्त सी बुक है, बट इट गिव्स यू लाइक हिस्टोरिकल पर्सपेक्टिव। सो इस तरह की बुक्स जो हैं, दे आर वेरी गुड, गिव यू अ वेरी गुड सेंस ऑफ व्हाट द इंट्यूशन बिहाइंड ऑल दिस कॉम्प्लिकेटेड फिजिक्स। अगर if you go and understand the actual science for the lectures, lecture notes कॉस्मोलॉजी के लेक्चर नोट्स हैं फॉर अंडर ग्रेजुएट्स। वो कैम्ब्रिज के एक प्रोफेसर हैं, डेविटोंग, प्रोफेसर डेविटोंग, उनकी वेबसाइट है, एंड यू कैन गो एंड हैव अ लुक एट। लेट मी सी कि मैं अगर मुझे कॉस्मोलॉजी सो मैं शेयर करता हूँ, ये लिंक मैंने शेयर किया है। these are the notes which are really good for the undergraduate level. Once you are comfortable with this course, I would suggest these lecture notes. These lecture notes will give you a very good overview. और इसके बाद ये लेक्चर नोट्स हैं जो प्रोफेसर डैनियल बाउमैन के हैं। डैनियल बाउमैन वाज एट कैम्ब्रिज यूनिवर्सिटी, बट नाउ ही हैज मूव्ड टू यूनिवर्सिटी ऑफ एम्स्टर्डम, and he's a superstar. He's a very young guy, very charismatic, superstar in cosmology. He worked on string cosmology while at Princeton. Then he moved to Institute for Advanced Study at Princeton, and then to Cambridge, and now at Amsterdam. So इनके जो lecture notes हैं, these lecture notes are for part 3 mathematical typos. Or part 3 mathematical typos is the master's course offered by the Cambridge University. And this course give you an opportunity to take as many courses as you want, and there are 100 courses you can take, 100 courses you can choose from. So lecture notes from David Tong are quite basic, and lecture notes from Daniel Bauman are very advanced, but it's a really good lecture notes. I don't think there are any other lecture notes which are better than Daniel Bauman's lecture note. These are classic lecture notes in cosmology. Once you understand these things, I can give you more link more complicated, more advanced lecture notes which can contain about large scale structure and perturbation theory and effective field theory and large scale structure. Okay, I think I'm still not the host, and I can't claim the host. Does anyone know how to claim host?
Sir,
host की
sir, I've asked Rida, वो आप host बना रही हैं 1-2 मिनट में बस, जितनी जल्दी हो सके।
Okay, चलें। So again, these two lecture notes are so some of the papers published in cosmology is not entirely but for understanding. I think that's a great idea. I have some good, very cool papers in cosmology as well, so I can discuss you. But let me just give you like some idea about what cosmology is, and then maybe at the end or maybe in the next series, I can give you some overview, okay, how to get sense of some papers. Because papers, if we discuss some papers right now, it will be very difficult for you guys to understand. So there are some books at the elementary level. There are 3 books which I can suggest to you. The one book is called Introduction to Cosmology by Barbara Ryden. This is a very clearly written book that presents an excellent, gentle introduction to the expanding universe with subsequent chapters on thermal history and structure formation. The other one is called an Introduction to Modern Cosmology. Okay, I think now I'm the host. I can share my screen. Okay, now you can see, right? The recommended books and resources. So second one is this one, Andrew Liddell, An Introduction to Modern Cosmology. So Andrew Liddell was one of the main figures, main persons who give the idea of inflation in cosmology. So he's very popular. And this gives you a very good introduction about expanding space-times, and so it's more qualitative and less quantitative, but it depends on what you prefer. Scott Doodleson, Modern Cosmology, again, is a very comprehensive, a classic book. Cosmology contains everything. Kolb and Turner, the early universe. Early universe, it talks more about the early universe, not the structure formation, not large scale structure, but what happened in the early universe, in the CMB and before CMB inflation. Steven Weinberg, if people know, Steven Weinberg is professor of physics at the University of Boston, and he won the Nobel Prize, and he shared the Nobel Prize with Professor Abdus Salam. He worked on the unification, and he has written a lot of books on quantum field theory, cosmology, gravity, some popular science books, even books on philosophy of cosmology. So cosmology की जो books हैं Steven Weinberg की, they are classic, and it's very, very comprehensive, very detailed, very comprehensive, because Steven Weinberg is a pure theoretical physicist, and he has written the book from a very theoretical physics perspective. It's not very applied, but it gives you a complete understanding of the mathematics and physics behind cosmology, but it's very hard to read, to be honest. So if you are very enthusiastic, then you can have a look at Steven Weinberg's cosmology. So again, the idea is in cosmology, we start with the Big Bang. What is the Big Bang? There's a misconception in the theory of Big Bang, because when we say the Big Bang theory, we are not referring to the time when the bang happened, right? So there was a point in the past when the universe was nothing but just a point, and there was like a mysterious bang happened, and all the energy was concentrated in this small point. And after it exploded, the universe started to form. But we don't know what happened and how did it happen, because all the concepts of physics, especially the concept of time and space, there is no concept of time and there is no concept of space at the time of the Big Bang. Everything is doomed. Even the concept of space-time, even right after the Big Bang happened, the concept of space-time do not exist. So we don't know about that theory. So when we refer to Big Bang theory, we don't refer to the theory of bang, right? When the universe started from a point, we don't refer to that point. What we refer to the point after 300,000 years after that bang, when the first hydrogen atom was formed. That point in the history of the universe is called the nucleosynthesis, and that was the point when the photons in the universe started to travel. Before that, everything was in a coupled soup, in a soup. Universe exists in a soup. Protons and electrons and even the photons, they were interacting with each other. But when proton and electron decided to form an atom, the photons started to travel. Okay. So that point in time, that theory, that nucleosynthesis is called Big Bang theory. So when we refer to the Big Bang theory, the point, is the time in the history of the universe when the first hydrogen atom was formed. Nucleosynthesis, Big Bang nucleosynthesis is generally referred to as the Big Bang. So we understand how nucleosynthesis happened. We can even observe the predictions of the Big Bang theory, the expanding universe prediction, the prediction of how many or how the concentration of different individual elements in the universe. We can measure that from experiments. So we have pretty good understanding of how did it happen, and we have theoretical as well as experimental evidences of that theory. But what happened before that point? What happened from the time of the Big Bang to 300 years after the bang? We don't know. We don't know what happened. So that time is called Dark Ages. But we do know what happened just after the bang, because if the universe was small, there were a lot of quantum fluctuations in the space-time of the universe, and suddenly universe started to expand. And not only expand, but the universe started to accelerate tremendously. So I'm talking about the time 10 to the power minus 43 seconds right after the bang. Universe went into the phase of accelerated expansion. And that small phase of the accelerated expansion is called the inflation. Universe inflated, universe expanded, inflated. And while the universe was inflating, all these quantum fluctuations in the universe get flattened out. What, Hassan? Do you have an answer? Question?
Yes, sir. Just confirming. Right after the nucleosynthesis, ये आपका इन्फ्लेशन होना स्टार्ट हुआ, मतलब उसके बाद की फॉरेन स्टेज ये थी.
No. So not before, not after nucleosynthesis, but right after Big Bang theory, like actual bang, right after actual bang, right after when the universe was 10 to the power minus 43 seconds old. Nucleosynthesis started to happen when the universe was 300,000 years old. Okay.
Oh,
And
right, sir. Perfect.
inflation happened when the universe was only 300, when the universe was only 10 to the power minus 40 or 43 seconds old. So that time, that period was crucial. Yes, sir.
सर आपने मेंशन किया कि लाइक 300,000 इयर्स के बाद वो हाइड्रोजन बना, तो उससे पहले यू यूज द वर्ड ऑफ सूप एंड कपल, सो आई एम जस्ट वांट टू कंफर्म, इज दैट बोस-आइंस्टाइन condensate?
Not Bose-Einstein condensate, but just a generic a soup, like coupled soup, a highly coupled soup of electrons and photons and protons. It's just a fluid. When there is no structure, there's no atom, but all these elementary particles are just freely traveling around, striking from, like, there is no interaction between each other, but they're just free. Okay, because photons were so energetic. Photons were so energetic when proton and electrons started to come together. Then photons are so energetic that they will always kick them, and they will prevent them to get closer to each other. So because photons were so energetic, electrons and protons were unable to meet.
So sir, even then, like there was a distinction between like protons and electrons, मतलब matter exist करता था वहाँ पे उस वक्त.
Yeah, the matter exists करता था, exactly. So matter exists करता था. Yes, Aliza.
So I wanted to ask, when we are discussing Big Bang, how do we create a distinction between cosmology and physics at the time of Big Bang? Because there was this book that I was reading, Brief Answers to Big Questions by Stephen Hawking. So उस book के अंदर it was mentioned that before we discuss Big Bang, if we discuss what happened before the Big Bang, so the singularity, how was it created? In the book, it was described that it was a negative web. So when we are discussing E is equals to mc squared, so we have a mass that is negative. So I think that was more of a physics aspect. But how do you, I mean, मुझे वो थोड़ी चीज अभी भी confusing लगी थी when I was reading that thing. So is there something, an explanation of something before the Big Bang, before the singularity?
So before the singularity, that's a very good question. Before the singularity, people have some. Okay, so the idea is that we don't know how did it happen. we don't know what was the state of before the Big Bang, because there was no concept of time, there was no concept of space, so we cannot say the universe was existing in some pre-space or pre-time scenarios. We don't know. We don't have even terminologies to explain. But some people have some ideas, some speculations. I cannot say these are theories, but some speculations. Maybe there were some multiverses where all these universes exist. But some very basic understanding, like some people can say, how is it possible that something can happen out of nothing? Okay, there is nothing, and you can create something. You can create energy, because the most fundamental law in physics is that the energy remains constant. The one form of the energy can be converted into the another form, but generally overall the universe energy remains constant. But before the time of the Big Bang, and when the Big Bang started, you can say, okay, look, I mean, there was nothing before that, and now there is something. So you're creating the energy. So how can you create something out of nothing? So the simple idea of physics explanation when that you mentioned, Elisa, is actually correct. People say that the universe. So we have not created some positive energy. There is some positive energy, but there is also a negative energy as well. So negative energy, they corresponds to the negative potential in the well. So the potential energy and the kinetic energy. If you combine all the positive and the negative energy, you will get the zero. So the overall in the ensemble of this universe, sorry, before and after, um, you get the overall energy of the universe is zero. But because we see one thing which has a positive energy, we think maybe there is a positive energy, so maybe there is a breaking of this law breaking, but there isn't. So there is some explanation, but still from the physics point of view, how did it happen? How can you explain these things? Nobody has any idea, and people are still working on these things. Okay, good. So inflation is happened. Inflation is very important. We don't know how did it happen, but we know like it did happen in the past, because it has some predictions on the later observables when the universe was in the form of soup, when the first hydrogen atom was formed, and that was the time when photons started to travel. And those photons we can still detect, and these photons are called cosmic microwave background radiation. And these photons contains a lot of information from inflation. So we don't know what happened when the inflation ended and the time when the photons started to travel. This period of time is 300,000 years period. We don't know what happened in that time. These times are called dark ages. But indirectly, because inflation has its imprints on CMB, cosmic microwave background radiation, we can learn a lot indirectly about how did inflation happen if you look into the data coming or light coming from the cosmic microwave background radiation. And this is what people do. People invent a lot of statistical estimators, statistical methods to extract those indirect signals from inflation, which can tell a lot about how did it happen, the physics of inflation. And if we can understand the physics of inflation at that high energies, because inflation happened at extremely high energies. So if you are aware of particle physics experiments at CERN, the physics, the energy of at which the experiments are run, these are almost 1.4 or 14 tera electron volts. But the energies of inflation were tremendous, 10 to the power of 16 giga electron volts, more than the energy of grand unification scale. So you learned a lot about physics at that scale. So our ultimate goal in physics to understand the theory of everything, meaning that we want to understand the singularity. So as we go closer and closer to the singularity, our understanding of the physics and the universe becomes much more sense. Okay. So we are still not there, but we can go more closer if we can understand inflation. And this is why this is the main motivation, one of the main motivation to study cosmology, because it can give you so much understanding of the physics, uh, very close to the singularity. You cannot get the grasp of the physics. You cannot understand what did it happen close to the singularity or Big Bang by studying or particle physics experiments at CERN. I mean, you can understand a lot, but still there is a limitation. How small, what small skills you can observe. But from cosmology, studying inflation and extracting the information about inflation from indirectly from cosmological observation, you can go really close to to understanding the physics of inflation. And this is one of the reasons that people still working on cosmology and trying to answer this thing. So I can talk about the current state of cosmology and the measurements later. But this is just to give you a why people do cosmology. So this is a graph of this is a plot of something called cosmic microwave background radiations, and this is what we refer to the Big Bang. So whenever I will say Big Bang, I'm referring to the Big Bang nucleosynthesis. Okay, so you have to understand the difference between actual bang and or the singularity and the Big Bang theory. So whenever in the literature people refer to the Big Bang theory, people refer to this time when the first hydrogen atom was formed and photons started to travel. Actually, the time when you can look at the cosmic microwave background radiations. So these are the lights which started to travel after the nucleosynthesis, and we can still observe these lights. And and these lights have been traveling for the last 13.6 billion years. So if we cannot see microwave from our naked eyes, but if we could, that at night we would see the sky something like this. Okay. Right. So there are two main assumptions in cosmology, what we assume, and these are very powerful assumptions. We call it the cosmological principles. Okay. And what are these assumptions? We assume that the universe is homogeneous, and we assume that the universe is isotropic. And these are very important names, even from someone who is interested in the philosophical aspect of cosmology. I can tell you these two concepts, homogeneity and isotropy, it's very important. I can explain in a while why these are very important from even philosophical point of view. So what is a homogeneous and isotropic? So homogeneity means that the homogeneity means that the universe is time translational invariant. What does it mean? That means that if I am observing the state of the universe from where I am now, right? And I move myself, I come to Karachi, and then I observe the whole universe from a big telescope from Karachi, I will observe the same universe. Okay, so my laws or underlying ideas, underlying principles in cosmology in the universe, my laws of physics will remain the same. So if I observe the universe from where I am currently in Geneva, or if I translate from Geneva to Karachi and I observe from Karachi, I will get the same image of the universe. So homogeneity. This is called homogeneity. I observe the one state of the universe from here. Yes, Susad.
सर आपने क्या वर्ड यूज किया टाइम ट्रांसलेशनल इनवेरिएंस रिपीट कर देंगे एक दफा
translational invariance, exactly. So time and space translational invariance. So time and space translational invariance means that if I translate spatially from here to Karachi, and then I observe the universe will be the same. And if I stay where I am in Geneva, and then I observe now, and then I observe maybe tomorrow, I will get the same overall image and same overall laws of physics, right? So this is what we call homogeneity. Isotropic means the universe is is the same in any direction you look. So if I look at in this particular direction, I will see the same universe. If I rotate, look into this direction, I will get the same universe. And this is called isotropy. Well, these two things will not make sense right now, because you can say, well, I mean, I am observing the universe in this direction. I am looking at, for example, my camera, right? Or my laptop. But if I look at in this direction, maybe I'm observing different trees or buildings in this direction. But what I'm comparing is the very small scales. Okay. On small scales, universe is not homogeneous. The scales of even the scales of a solar system, even the scales of galaxies, universe is not homogeneous. It's not isotropic, because maybe if you look at in this direction, you will see some stars. You will see this direction, you will see like different concentration of stars. But it depends on the scales. In cosmology, what we consider huge, massive scales. We don't consider only solar system and galaxies. We consider clusters of galaxies, distribution of galaxies. And I will give you some sense of the scales in cosmology. And that on cosmological scales, the universe look like almost the same thing. And I will tell you later, then when we consider in cosmology those massive scales, um, most we even can consider the whole galaxy as a single point particle, right? Galaxy is massive, right? Even our world is massive, Earth is massive, solar system is massive, sun is massive. Imagine galaxy is massive. Galaxy contains 400 billion stars like our sun, and sun is massive. And you can imagine like how big the galaxy is. But in cosmology, this whole big galaxy is just a single point particle. We have like billions of galaxies in this distribution. And when we consider the billions of galaxies, then we do an approximation. One of the approximations we use in cosmology is we use a fluid mechanics. We assume that the universe is so massive, there are more galaxies in the universe than maybe number of atoms in your water glass. It's so massive that you can apply the idea of fluid mechanics in cosmology, and you can say, well, maybe if you consider one galaxy is a single point particle and there are billions of galaxies, then perhaps the universe is behaving like a fluid. On that massive scales, perfect is like a perfect fluid, right? So if you take a glass of water, you will see that it looks very smooth, right? It looks very uniform everywhere. But if you go deeper, if you go at the molecular and atomic level, you will see that one molecule of atom is here, the other molecule of atom is here. There's a lot of space. So on the molecular level, the uniform water will not look very uniform. But on a macroscopic scale, when you can observe from outside, the water look very smooth. And this is the same assumption we apply in cosmology. And this is very important. And this is the beauty of physics as well. The beauty of physics is that we understand how to apply good approximations and good when we can assume things and make a model which is very simplified model. We can take a very complicated thing like the universe, and we can simplify it in is as simple as like a water description, a fluid description. Yeah. Yes, Hassan.
सर एक थोड़ी कंफ्यूजन थी आइसोट्रोपिक और होमोजेनिटी में। आपने बात की कि आइसोट्रोपिक में इट शुड अपीयर द सेम इन ऑल द डायरेक्शंस, किसी भी डायरेक्शन से हम रोटेट करके देखें तो आइसोट्रोपिक में हमें सेम नजर आना चाहिए। होमोजेनिटी में आपने कहा कि अगर आप यहाँ अभी जिनीवा में बैठे हैं, आप कराची आके देखते हैं तो यूनिवर्स को वैसे ही नजर आना चाहिए। तो क्या हम इसमें कॉम्पोजिशन की बात कर रहे हैं कि यूनिवर्स का कॉम्पोजिशन वैसा ही होता है हर जगह पे?
The state of the universe, right. अगर आप एक big massive direction में number of stars and galaxies and the so अगर if I want to understand, if I want to calculate the number density of matter, ठीक है, from Geneva, and I observe the number density of matter in the universe from Karachi, I will get the same result. That's what I'm saying. Okay. Or if I
Perfect,
look
sir,
at,
got it.
if I calculate the average temperature of the whole universe from Geneva today, and the average temperature of the whole universe next year from Karachi, these are two different different states, right? I will get the same result. And this implies homogeneity because this universe is a homogeneous. So it's the same from every location. And isotropy says that it's the same in every direction. Okay. And if you
Perfect,
assume
sir.
the universe is homogeneous and isotropy, every single point in the universe, is the center of the universe. Okay. So this is
Oh,
very
interesting,
important.
right?
This is very important to understand that there is no special center in the universe. Every single point of the universe is the center of the universe. Because wherever you go in the universe, whichever direction you look at, you will see the same composition of the universe, right? Universe will look the symmetrical in every direction you will. So we say that because of homogeneity and isotropy, universe is the same. So this is a really good assumption, homogeneity and isotropy. And maybe I will show you, but if you go more deeper into the research, if you try to understand galaxy formations and even understanding the clusters of galaxies, you assume inhomogeneities in the universe because on those scales, the universe is still not homogeneous. So you assume a lot of inhomogeneities, and inhomogeneities include complexities. So your model become more and more complex. But the good news is that you can still apply the idea of fluid mechanics. So the most simplest of the fluid. So how can you describe a fluid? You can describe a fluid from its viscosity, its density, okay? How dense the fluid is. Maybe oil is more denser than water, so oil will always float at the surface of the water. Because how can you differentiate what is oil and which one is water? You differentiate using densities. The density of water is different, density of oil is different, maybe the viscosities are different, viscosity of water is different, viscosity of oil is different. So these are some macroscopic parameters in the fluid dynamics, which describes the whole fluid, which differentiate different fluids from each other, right? And this is the beauty because this fluid dynamical, this macroscopic coefficient like viscosity and density, it contains all the information about the molecular interactions, about how the molecules in a fluid are interacting with each other. And but the beauty is you can just identify some parameters like viscosity, density, uh, and these parameters. You can measure these parameters from experiments, and then these parameters will help you differentiate between different fluids. But the beauty is these parameters contains all the microscopic description of the fluid. So you will not have to go deeper, like you don't have to consider 10 to the power 20 or 40 molecules interacting with each other and then solving that complicated system. You don't have to do that. You can assume you can assume some parameters in fluid and then measure those parameters, get the sense of what the values of those parameters are. And these parameters contains all the information about everything happening at the microscopic scale. Okay. And this is the beauty of the modeling. And this is what we also apply in cosmology. We assume that the universe is all homogeneous and isotropic. We can model it as a perfect fluid. And when we consider the perfect fluid, we only need the density of the fluid and the pressure of the fluid. Okay. So these two parameters are very important. And I will show some equations. You will see the density is very important. Wherever we talk a lot about the density. Even when we apply complicated mathematical models, we always use the parameter density parameter. So density of the fluid, pressure of the fluid, when the universe is when the fluid is perfect fluid, when the universe is homogeneous, fluid is the homogeneous, perfect fluid. We we describe these things. We cannot visualize the pressure of the universe. I will tell you later. But these are the new concept. I mean, it will take some time to get the intuition how to analyze the pressure. But when I'm telling you the pressure and the viscosity and the density, density makes sense intuitively. Pressure will not make sense right now because because most of the things are models, right? So I am also telling you how we can model, how we can understand this complicated system, right? So this pressure is just the modeling parameter. Okay, so yes, Susad.
अच्छा सर, आपने थोड़ी देर पहले जब मैंने पूछा था तो यू सेड टाइम एंड स्पेस ट्रांसलेशनल इनवेरिएंस। आई थिंक यहाँ मैं जो पढ़ रहा हूँ आपके जो हाईलाइट के नीचे लिखा हुआ इट सेज कि आइसोट्रोप इन टाइम नहीं होता, वो सिर्फ स्पेस होता है गैस।
या ओके, स्पेस होता है, ठीक है। But
Because
the
वो
laws
evolution
laws of physics are also time translation invariant.
ओके एंड अनदर क्वेश्चन वाज कि अच्छा आपने ये क्या कहते हैं जब कॉस्मोलॉजिकल प्रिंसिपल बताया तो यू सेड के दीज आर द assumptions we take, so like coming from a mathematical background my question is that are these like axioms कि हम ये assume करके फिर थ्योरी बनाते हैं उस पे हम इसको प्रूव नहीं कर सकते?
Yeah, so these are the assumptions. These are assumptions, simplified assumptions, but you have to start from a simplified model, right? So these are okay. This is also a good point. These are isotropic and homogeneity in space. These are spatial homogeneity and isotropy, but in time these are not homogeneous because आप कहोगे कि 1 billion years ago I have the universe की concentration was different, but the density has evolved now because all the structures are forming. The universe is expanding. The universe may not look like the same in time because of the structure formation, but in space, the universe, because you take this one snapshot at one time, take the cube at the one time, and then look at the universe from every direction and every point, then the universe will look like the same. And these are the assumptions. Yeah, you're right. These are the assumptions, but these are good assumptions, and that's what we do when we study a very complicated system. We try to simplify the system using very simple assumptions, and it works. It remarkably works very well everywhere. Okay. So this is what we look. This is what it looks like. The distribution of galaxies in the sky. So this is an old image taken from a galaxy survey, and we can. So there are two main observables in the universe, right? So the one main observable is the light coming from the Big Bang. This one, it tells you what happened in the early universe, 13 billion years ago. The second main observable in the universe is the distribution of galaxies. But this observable is the late time observables when the structure started to form in the universe. Okay, so you can consider that how the galaxies are distributed in the universe, and this distribution can gives you a lot of information about the initial conditions, the evolution of the universe, and everything. But there is a difference. There's a trade-off between which observable to use. So cosmic microwave background radiation (CMB), it's very simple. It's homogeneous. You can apply the physics of light to understand different variations in CMB, but it's a two-dimensional image of the three-dimensional universe. Is an image is on the surface. You only look at the surface, and because you're going from 3 dimension to 2 dimension, you are losing a lot of information because you are going from a higher dimension to a lower dimension, right? So because so what are the pros of using CMB? It's a very simple model. We understand everything about light. We understand the cosmological perturbation in CMB, but we do not have access to a lot of information because of the dimensional reduction. Whereas in the distribution of galaxies, it's a late time phenomena. It is more complex than the CMB because you have a lot of non-linearities, a lot of complexities, but it's a three-dimensional image because you can observe in the three-dimensional, you can observe the three-dimensional universe. So dimensional reductions means going from 3 dimension to 2 dimensions. So 3-dimensional universe, you're projecting it to a 2 dimension, and what you observe in the sky, cosmic microwave background radiation, it's a 2-dimensional image of the universe from the Big Bang. Okay, so this dimensional reduction going from 3 to 2 dimension loses a lot of information in CMB. So you gain a lot of information in the galaxy clusters because of 3-dimensional survey. The only problem is that we have limitations. We have technical limitations how far we can observe. So one is the technical limitation because we can only observe the small fraction of the universe in the galaxies. But for the CMB, we can observe the whole history of the universe. See, the lights have been traveling from the time of the Big Bang till now. So they have seen everything happening in the universe. So they have information about all the structure formation in the last 13 billion years. So they contains all the information. Whereas, so you're observing the whole fraction of the whole universe through CMB, but you have less information because of the dimensional reduction. Whereas in the galaxies, you have a lot of information because of the 3-dimensional survey, but you have limitation, technical limitation, because you're only observing the small fraction of the sky. Yeah.
सर सो मुझे बस थोड़ा सा टेक्निकली समझ नहीं आ रहा है कि अगर आपके पास जैसे फॉर एग्जांपल ऑब्जर्व कर रहे हैं तो लाइक फोटॉन्स आ रहे होंगे, ठीक है, अल्ट्रावायलेट या जो भी आप उसको जिसमें भी डालें, सो लाइक व्हाट्स द डिफरेंस, आप कैसे ऑब्जर्व करके बताते हैं कि ये CMB से आ रहा है और ये अभी लाइक ये कल परसों की गैलेक्सी से, हाउ व्हाट्स द टेक्निकल थिंग, क्या ऑब्जर्व हो
So
रहा है?
these are called spectroscopic techniques or frequency techniques in CMB. I'm not an expert in the CMB analysis, but people use different frequencies of frequency plotting. So they observe all the frequencies of the light, and some frequency range will correspond to the CMB spectrum. So they discard all the light and they will only focus on one frequency, and they actually design their experiments in a way then those experiments will only observe those frequencies. In electrical engineering, you have read about frequency bands, right? Low pass, high pass, mid pass frequency. So you only observe one fraction of the frequencies, but you discard all the other ones. So whichever, so the light, for example, how you observe the galaxies, you observe the galaxies also from the light. So there are two ways you can observe the galaxies. One is called the spectroscopic survey. In a spectroscopic survey, and the other one is called the photometric survey. In the photometric survey, you have gigantic telescopes, and you take the snapshots of the sky. And the snapshots, how deep the snapshot is depends on the focal length and your camera, but they can go really, really deep because technology is advancing, and you can take a really good, really deep snapshots. But these are two-dimensional snapshots. You can take the two-dimensional snapshots. You can construct a three-dimensional survey. These are the photometric survey. In spectroscopic survey, you observe the light coming from different galaxies. And because when the light travels, it loses energy. When it loses energy, its wavelength gets stretched out. And we call it a Doppler effect, Doppler shift. So think of it as like when you hear a car coming towards you with a siren, you increase a high pitch, like sound is increasing, the frequency is changing. It's a Doppler effect. So, okay, so it's called a redshift effect, sorry. So Doppler effect is what, when the, so the good thing is that we can observe it through the redshift, but there is a problem. The problem is the Doppler effect. What's the Doppler effect? So individual galaxies are moving also locally, right? So when the galaxies are moving locally, if you're observing the galaxy in this direction, and if the galaxies are moving towards you, then you will see a different shift in your redshift. Okay, And that shift in the redshift comes from the Doppler effect because of the local movement um, of galaxies. And this is really complicated problem. Yeah.
So almost everything is redshift, but some are less redshift because of local movement. Is that what you're saying, sir?
Yeah, so redshift and blue shift, generally we have redshift and blue shift. Redshift is when you're so depending on something is coming towards you or going away, it's a redshift or blue shift. But locally the galaxies are moving. So galaxies can be moved in any random direction. So if it's moving towards you, or if it's moving away from you, that introduces a different shift in the redshift of the galaxies. Either it increases the slight distortions in the redshift. Either it increases the redshift or decreases the redshift. But this phenomena, I'm saying, I'm not going deeper into this phenomena. This is called red space distortions. So when you observe a galaxy and you observe the redshift, you can interpolate how far the galaxy is. But because of this Doppler effect, local movement of galaxies, the reconstruction is not the exact reconstruction. So you don't know where exactly the galaxy is because of those small distortions. And this is a really complicated thing to model in cosmology. And therefore, because the galaxy surveys provides you a really good information because a three-dimensional survey, but it's a really complicated model thing to model because of this redshift space distortion, because you don't know the velocity distribution of galaxies, right? So you have the CMB. Yes, I think, Mirza, do you have a question? No. So in CMB, you have a lot of information. CMB is very simple. You know how to model it. It has information about the whole universe, but because of the dimensional reduction, we are losing a lot of information, and because of the technicalities. On the other hand, the galaxy surveys contains a lot of information, potentially a lot of information. Three-dimensional survey, there are two problems. One is that because of technical problems, we can only observe the small fraction of the sky. And second is because the modeling of redshift space distortions, how galaxies are locally moving around each other about their own point. It's very hard to model because it introduces distortions in your reconstruction. So these two complication problems, one is a theoretical modeling, the other one is experimental and technical limitations. And because of these things, there is a problem, and still people are working on galaxy surveys, galaxy clustering, and there are a lot of chances of improvement because we have not exploited all the information, and this time is just the beginning time to do more and to understand more about galaxy clusters and galaxy surveys. Yes, Hassan.
Sorry, sir. अगर आपको लग रहा है questions ज़्यादा पूछ रहे हैं, तो we could maybe limit our questions. But I had.
It's okay.
Perfect. So, sir, I was reading this recently, a research article on cosmology, which was published in Scientific American. So there's this student at UC Irvine. She was working on her PhD thesis when she came across one of these galaxy clusters, जिनको वो red dark clusters कहते हैं. Have you heard about them?
No.
Okay, so what happens is that those galaxies have a very short lifespan. So they like come into the universe and then they die like within 300 million years, which is much smaller than our the life period of our galaxy. So like it was there in that research article that our current understanding of physics cannot explain such quick growth of these galaxies. And also that उसमें ये भी था कि there was just one more point ये था कि these such galaxies have been hidden from the view of scientists, because like they form so quickly, और जो उसमें star production होती है, that is so intense कि उसकी वजह से there is a lot of production of, I don't know, some metal, which like makes it difficult for us to spot those galaxies. So like this is another problem in identifying such galaxy clusters.
In astrophysics or cosmology, understanding the formation of galaxy formation process, no one knows. It's an open problem in cosmology. Even we do have some simulations about galaxy formation. People have been working on these simulations now, but we don't know. It's a very, very, very complicated problem. We don't know the physics of galaxy formation. It's a really complicated problem. So yeah, there is a chance that there are some clusters of galaxies which we don't know. So we don't know. In cosmology, the thing what I'm trying to explain in cosmology, you don't have to worry about how the galaxy is formed, okay? Because in the cosmology, our main goal is to measure some parameters. So precision cosmology, you take the observable, you want to measure some cosmological parameters, and the measurement of the cosmological parameters tells you about which model of the theory and which model of the universe is the correct model. So while doing that, we do a lot of, yes, Hassan. Hassan, your
नहीं sorry sir, वो lower hand करना मैं भूल गया था. I'm really sorry.
Okay, so because of this, we have those limitations. We have the problem. So in cosmology, because we don't know about all the galaxy formation and everything, we assume it's a point particle. We assume a fluid dynamical description, and then later, maybe if I get a time, later lectures, I will describe you how can you and you can use some framework and encapsulate all your ignorance in some parameters. So if whatever you don't know about galaxy formation, you can assume a model in which you have number of parameters which contains all the information about everything at the galaxy level, and these models these parameters you can measure from the data, and that's it. It's just like the fluid. But I will talk about later. I think it's a very complicated thing. It's a very beautiful framework, but it's a bit complicated to discuss it right now at this time.
Perfect. So thanks.
Okay, so the sense of scale, but there's a lot of what I'm trying to say. There are a lot of open problems. It depends on what scale are you interested in. If you're interested in cosmic scale understanding, then of course this is what I am telling you. The universe is like this. You can make these assumptions, and the main aim of doing cosmology is to understand the physics of inflation, understand the evolution, and different parameters to measure. So mostly parameter estimation and precision cosmology, how to understand the physics from the data. This is what we. But from the physics point of view, you have a lot of problems. If so the physics of the galaxy formation, no one knows. So you can study. There's an open problem in cosmology and astrophysics to understand how the galaxies are formed. And if you can study, if you can make simulations or help people make perfect simulations to simulate how galaxies are formed, then it will be a huge favor in the community, the scientific community. So sense of scales, we use the scales called astronomical unit. Okay, so one astronomical unit is equal to 1.5 into 10 to the power 10 meter. And we also use light years. In light year, 1 light year is the distance traveled by light in 1 year. So the light has been traveling, and if it covers the distance of 9.5 into 10 to the power 15 meters, you will say it's a 1 light year distance. Okay, so we define astronomical unit like this. So a lot of people in astrophysics use astronomical units, AU. In cosmology, we actually use megaparsec. or parsec, because it's a huge scale. So astrophysical scales are relatively smaller. So people still use light years and AU, but cosmological scales are massive, and therefore I'm taking it. So one astronomical unit is 1.5 times the power 11 meters. One light year is the distance traveled by light in 1 year, which is then 9.5 times the power 15 meters. And I can give you the sense of like how the speed of light. 8 minutes, the light can travel from sun to the earth. It takes 8 minutes for the light, and in 1 second, the light can take 3 rotations around the earth. So that's that is the speed in 1 second. If you go 3 times around the earth, 8 minutes you can go from sun to the earth. Then imagine like the distance the light travels in 1 light year. 1 year is 1 light year. Okay, and if you also define the distance called parsec. So 3.26 light years, the light which travels 3.2 years, the distance it covers is called 1 parsec, right? Okay, now you get the sense of what 1 parsec is. Our closest neighbor, this galaxy, our closest galaxy neighbor sits at a distance 1.3. It's not a galaxy, it's a star. This Proxima Centauri sits at a distance of 1.3 parsec. So if we want to send a signal from Earth to Proxima Centauri, it will take almost 4.5 light years. So if we send with a light signal, it will get up. It will reach after 4.5 years. The distance to the center of our galaxy, so from where we are to the center of the Milky Way galaxy, is 8 kiloparsec, which means 8 kiloparsec means light will travel for 8,000 years. Imagine it will take the light 8,000 years to go from where we are to the center of our galaxy, and this is just one galaxy. 24,000. Thank you. So yeah, 10 to 94,000, 8 multiplied by 2. But 24,000 years it will take light to go to the center of the galaxy. And our galaxy is home to around 100 billion stars. Okay, this is what I'm saying. And it's approximately 30 kiloparsec across. So from one point of the galaxy to the other point, 30 multiplied by 3, 90,000. It will take the light 90,000 years to cross the Milky Way. Just one galaxy. And we don't talk, and the scales we are talking about in cosmology is not kiloparsec, it's megaparsec, right? So 1 megaparsec on 1 million parsec. And imagine the light, it takes 1 million years, right? 1 million years to travel. The distance it will cover in 1 million years is called 1 megaparsec. And this is the smallest unit we use in cosmology, megaparsec. Got it? So just assume, just play around the scales that we're talking about. It's so massive that we cannot imagine the scales of the universe. It's so massive. Like just imagine just one galaxy. It will take 90,000 years light to cross one Milky Way. And I told you in the beginning that in cosmology, the scales are so massive. There are so many galaxies. There are billions and billions of galaxies and the clusters of galaxies that we assume a single galaxy as a point particle, right? A small particle. We can use that approximation that the galaxy is a point particle. So assume or imagine the scale of the universe. Be amazed. It's a really amazing thing. I don't know, like I cannot imagine. It's really, really massive. I cannot emphasize enough. You just have to imagine more and more and play with these numbers, because these numbers are just mind-boggling. The universe is so vast. It's a miracle. to be honest. So galaxies are not the largest objects in the universe. They in turn get it into clusters. So this is a very interesting concept in cosmology, because galaxies are not uniformly distributed. Galaxies are distributed in clusters. So when we talk about the galaxy distribution, we talk about the clustering of galaxies. And galaxies are social beings. They're not introverts, right? So they want to live in families. They want to live in communities. So you will see, if you observe, you will find a cluster of galaxies here. You will find a cluster of galaxies there. Some clusters are small, some clusters are big, and there is a reason why galaxies live in clusters. And I will talk about this. What's the reason when I tell you what the large scale structure is, and I will show you some simulations maybe later lectures. But just to give you an idea that galaxies are always living in clusters. You can never find a single isolated galaxy, or you will never find that the distribution is uniform across the universe. It's not uniform. And this is the beauty. This is why I was telling you it's very interesting, because you can have a lot of understanding about what are the initial conditions. So given this initial conditions, the clusters and distribution of galaxies is this. If you change the initial conditions, the universe, the structure formation will be changed, and the distribution of the galaxies will be changed. So by looking at the distribution of galaxies, you can actually tell a lot about the distribution and the initial conditions. But there is some problems I will tell you, because you cannot directly tell everything from the distribution of galaxy. You have to go one step further, because you have to go from the galaxy distribution to the underlying dark matter distribution, and the dark matter distribution actually tells you a lot about the other things. But these are some complications in the modeling of the galaxy clustering. But I'm telling you, the galaxies always live in clusters, and these are the scales, megaparsec scales. So we talk about 100 megaparsec, 1000 megaparsec, stuff like that, gigaparsec. So for example, the current cosmological survey, the current galaxy surveys, the range of the scales they can observe is 1 gigaparsec or 9 gigaparsec, 1 to 9 gigaparsec they can observe, right? So it's massive, and it's still not the whole universe. 1 gigaparsec is not the volume of the universe. Gigaparsec cube is not the volume of the universe, but this is the observed volume, current observed volume of the universe. So this is just an image from the Hubble Ultra Deep Field, shows around 10,000 galaxies. This is 1 clusters of galaxy. We can. Okay, so this is just the size of the universe. So this is the quote by Douglas Adams. It says, "When you are thinking big, think bigger than the biggest thing ever, and then some. Much bigger than that, in fact. Really amazingly immense, a totally stunning size, real. Wow, that's the big time. It's just so big that by comparison, bigness itself looks really tricky. Gigantic multiplied by colossal multiplied by staggeringly huge is the sort of concept we are trying to get across here. So it will take some time to develop some intuition about how massive, like big scales we are talking about in cosmology. So I think we can finish in 10 minutes. I can show you some slides. Let me show you some slides and give you some more overview of. So this is one slide that I wanted to show, just to give you an idea of what we do in cosmology, and especially large-scale structure cosmology. So imagine you have the inflation, right? Or I have to show. I think this figure might look a bit difficult to understand, but let me see if I have another figure. This is from the modeling perspective. I think I have another talk somewhere. Okay, yeah, I think I have another one. Okay, so okay, so this is what I'm talking about. So what we do in cosmology and what we want to learn from cosmology, we want to understand origins of the universe. Okay, so from the origin of the universe, I mean the dynamic of the universe, and how we can learn from the dynamic of the universe. We want to measure something called primordial non-Gaussianity from the data, from the cosmological data, and measuring and the value of this parameter will tell you the physics of inflation. We want to understand dark matter in the universe. There is 27% of the volume of the universe consists of dark matter. We want to understand the nature of dark energy or the modified theory of gravity. Almost 70% or more than 70% is this dark energy in the universe. And we can tell a lot about the expansion history of the universe. There is one thing that I will show. There's a big problem in cosmology at the moment called Hubble parameter Hubble parameter problem. Neutrino masses, so we can tell a lot about the neutrino masses. Again, a big problem. Galaxy formation and late time structure formation, and of course, you want to understand the fundamental laws of it. So this is what I was trying to show you is this is the image of the universe, the expansion of the universe. So this point you can see. So this point this point is the Big Bang, is the initial low energy state, right? The quantum fluctuations. You can see the space-time expanded tremendously, right? So this is the phase of inflation, and the inflation ended, universe is cooling down. This time from here to now to this CMB is called dark ages. We don't know about these things. And this thing happened, the universe became transparent at 380,000 years after the Bang. So inflation, initial low state energy, quantum fluctuations, Big Bang nucleosynthesis, CMB. And after there is another dark ages because we don't know what happened after this thing. And then when the universe emerged from the dark ages, the first stars were formed 400 million years after the Bang, and the stars formed the galaxies. Then the galaxies formed the clusters of the galaxies after 2 billion years, and then the pulsars are formed, the standard, which are the standard candle, which defines the brightness in the universe. Then the supernovas are formed. The universe went in from the radiation domination to the matter domination, and from the matter domination to the dark energy domination. There are three phases in the universe. The phase when the universe was dominated by radiation, and then the phase there which universe was dominated by matter, and then the phase which we are currently living in is the phase when the universe is dominated by dark energy. And dark energy is the responsible for the expansion of the universe. The galaxies are formed and everything is. So we are living here in 13.8 billion years after this thing. And this phase that we are living in is also very special because it's very similar to what happened to big inflation. In inflation, the universe is accelerating, right? And because of dark energy now, the universe is also accelerating again. So we are living in kind of an inflationary scenario. And this is what I was trying to tell you. So what is the difference between using cosmic microwave background radiations and using galaxy clusters? So as you can see, from zero till now, so the CMB covers the whole expansion of the universe. It covers the whole universe, what happened in the 13.6 billion years from now. So this is what we observe. But you can see that it's a slice. It's a two-dimensional image. It's a projection of the three-dimensional universe. So what we are observing in cosmic microwave is the projection of the universe. It's a two-dimensional image that we observe. Whereas you can see in this SDSS survey, Galaxy Survey, Sloan Digital Sky Survey, it only covers from say 7 to 13. It only can do 6 billion years. It can only observe a small fraction of the universe. There's a lot they can observe, but we are limited from technology. So maybe in future when we have massive surveys, and now in the next 5-10 years, the new surveys which they are working on, they can observe more fraction of the sky, more fraction of the volume of the universe. It can give us a lot of information about, because three-dimensional. And people are also trying to look into this area called intergalactic gas, which also contains a lot of information. So combining different observables, they are increasing the number of information. So therefore, the current focus is not on the CMB. There are some small problem people still want to extract from the CMB data, but most of the information have already been extracted from CMB observables, right? So most of the current research is focused on this galaxy clusters. How can we understand the galaxy clusters from theoretical point of view, from simulation point of view, and how can we analyze these massive amount of data coming from galaxies and extract more information and improve the results from cosmic microwave background. So most of the research is focused on galaxy clusters, and this is what we call large scale structure, right? Okay. So just the last last slide, and then we can stop for now, is this thing. So when I talk about how we model, how we study all those things, we go from inflation to the initial conditions. Inflation provides initial conditions. From initial conditions, we get something called non-linear metal density, and there are some analytical ways to understand this relation, and there are some simulations which you can do. From non-linear metal density, you get something called dark matter halos. These are the structure of dark matter in which galaxies are formed. And you can also identify these structures in the initial conditions, which will later form into dark matter halos. And once you have dark matter halos, you apply some technique called halo occupation distribution, which assigns the number of galaxies given the like if you have certain mass of the halo, you can assign how many number of galaxies this halo can accommodate. And once you have the rest frame galaxy statistics, you can include the effects called projection effect or the redshift space distortion effect, local movement of galaxies I described earlier, to get observed galaxy statistics. So we have the roadmap from going from the initial conditions to the observed galaxy statistics, and how can you model using analytic expressions and using simulations, which we can maybe talk later. But also the current state of the the current state in the research in cosmology I was telling you is actually applying the idea of machine learning to extract information about the initial conditions and other things. So how we can do that, I can also tell you how we can use the idea from cosmology to solve some problems in computer science as well, in deep learning AI, and how can we apply the idea from deep learning and AI to cosmology to improve the constraints. So there are some recent advancements that I can also talk later. But this is just a generic overview of what the cosmology is. What are the scales that we are talking about? What is the aim of the cosmology? What observables are important in cosmology, and why one observable is better than the other? And what are the pros and cons of using the observables to extract information? So this is a generic overview. I haven't talked about the mathematics of cosmology. I haven't talked about, when I say the cosmological parameters, what are those cosmological parameters are, why are they important, how can we know which one is important to extract, and I haven't talked about how can we apply the idea of fluid mechanics. I haven't talked about the idea of perturbation theory and how can we get from theory to predictions. But this is what cosmology is actually, is you have the theory and how can you go from theory to predictions, and from predictions to actually apply the idea to simulations and data analysis. And there are so many interesting things, of course, but we can see what we can discuss later. If you have any suggestion, if you have any questions, if you want me to discuss something, come up with some suggestions. Tell me, and we can discuss. So, any questions? Was it too technical for you, or was it too easy but too technical? Tell me, like, how was it, so we can try to improve these lectures.
Sir, let me start. Sir, I think perfect. The lectures were perfect. The difficulty level was really, I mean, exactly what I had hoped for. Or I think anybody with even a slight understanding of physics could have easily followed this. So I think difficulty level exactly यही रहे तो बहुत अच्छा है. So it would be easier for all the students in the class to follow. अच्छा सर, एक और बात सर ये थी कि external students का ये है कि they couldn't join this time because like we did not really open the registration for them. और next week से तो आप उनको भी देखेंगे. तो अभी सिर्फ क्लास में there are only Habib University students.
Okay. I think if the pace are okay, and we can then keep that pace and keep this information. And I will try to make it as simple as possible without showing you a lot of equations. Or if I show you some equation, I will try to give you the sense of how to get intuition. But what I'm trying to say is people from computer science background, they are actually pretty ready. You can keep working in cosmology and astrophysics. So one of the projects I'm working on right now is this institute in New York called the Flatiron Institute, and it's a really famous institute focused on computational sciences. So they focus on computational astrophysics and cosmology and data analysis, computational biology, mathematical analysis and stuff. And so one project I'm collaborating on is 6 people from different backgrounds, so cosmology background, people from data analysis background, and machine learning background. And there is one guy who's also working at Flatiron. Flatiron is very prestigious, so getting like a full-time fellowship there, it's very competitive. So one guy at Flatiron, which is involved in this project, he came from mathematics background. So he has no understanding of cosmology, but he is able to do research in cosmology because he has understanding of statistics. So people who with a CS background, with people who actually know how to do data analysis, people who know like how to use deep learning, how to construct convolutional neural networks, they are pretty valuable in cosmology, and there are a lot of problems they can do right now. And but we can talk about these things later lectures. Okay. Any question?
Perfect. Guys, do you have any questions?
No. So, okay, thank you very much for joining.
And sir, just one more thing. A few students couldn't join this time.
Okay.
Because they had exams. Like
ठीक.
exactly during this hour they had exams. तो वो उस वजह से join नहीं कर पाए, तो वो recording देख लेंगे और फिर वो next week से join कर लेंगे.
चलो,
So like
okay, no problem.
ये कोई 3 4 5 बच्चे थे जो नहीं join कर पाए. So we'd have a very like अभी we had like 15 students, तो फिर हम expect कर रहे हैं और ज्यादा होंगे, फिर external students आ जाएंगे तो और class ज्यादा बड़ी होगी. You don't have a problem with that, right?
हाँ, I don't have a problem. कोई मसला नहीं है. चलो ठीक है. इस तरह काफी. But next time we will see each other again. So 2:30 का. How about 3 p.m. 3 p.m. सही रहेगा? या late हो जाएगा काफी?
नहीं sir, it's perfect for us. Whatever is convenient for you.
अगर 3 p.m. next time से कर लोगे तो वो थोड़ा सा बेहतर है, क्योंकि यहाँ पे 11 होते हैं, which is okay, but Saturday को मैं थोड़ा सा मुझे
A little early. Right sir. Sure, no problem sir. So we will set up the meeting for 3 p.m. from next week onwards.
ठीक है. Okay. ठीक है.
Thank you so much sir.
Have a good weekend and see you next time.
See you sir. Khuda Hafiz.
Bye. Khuda Hafiz.
मीटिंग कैंसिल कर दो.